Okay, proceed. Hello everyone. So today we will go back to optimization for a little bit, and we will cover this algorithm called descent. So before I describe that, let me first say why you want something like this. So here is an example. So let's just recall our setup for gradient descent. So we had a function which perhaps is smooth. So let's call it L smooth, and maybe it's convex also. Yeah, and now you want to minimize it, and perhaps you started R away from the minimum. So the distance between your initial point and your minimum is, let's say, R. Then if I do gradient descent with step size roughly 1 over L, then I can get a guarantee of the following form: f of xt minus f of x star. So that's how far away I am from the minimum value. That's at most roughly. Okay, anyone remember? Yeah, exactly. So you get 1 by t. Yeah, and due to the dependence on R and L, sorry? Yeah, to R and L as well. Yeah. Yeah, so you get something like this. Wait, am I made a mistake or is it right? Yeah. Sorry? Yeah, it's fine. Okay. Yeah, so get something like this. But now you might ask that what is a typical L here? So here we're pretending that L is a constant, so we're kind of ignoring it. But suppose your function is such that the gradient is maybe bounded in the so maybe each coordinate. So maybe the infinity now is bounded. Maybe there's at most one. So then the L2 now, which is like the Lipschitz constant, is going to be, yeah, this could be as large as root t, right? Where t is a dimension. So even though this L is looks very innocuous, it looks like a constant, but actually, if your function is has an infinity bounded gradients, then this norm here, the description of here could be really large. So then naturally one could expect that hey, can we get similar bound? So it's a similar bound, but with the infinity norm instead of right? Yeah. So yeah, more precisely, one could ask for the or in terms of the Lipschitz constant in an arbitrary norm. So yeah, so more generally, so okay, so this is kind of the motivation. And yeah, so now let's build some machinery so that we can actually get to this point. Okay, so first I talk a little bit about duality for a little bit, just to build the background, and then yeah, we'll come back to this. So, so we'll talk about a particular kind of duality called conjugate duality, which maybe you already know, but just to remind in case you don't know. So, okay, so this is going to be just some theory. So let f be some function from Rd. Okay, well, okay, this is it's from Rd to R, and yeah, and then let's define f star to be the max of x minus yeah. And by the way, just to help things a little bit, we will do some cheating and we'll also include infinity in this range. So if the function can go to infinity, or this just put infinity here. And similarly, f star can also be. Because it's just to basically to avoid writing too much detail. Yeah. Slight abuse of notation. Okay, so this is how we define the dual, and it's a many names. It's called the convex conjugate. In some books, other books call it Legendre Frenchel transform. It's also called the Frenchel dual. Yeah, so all kinds of names. Okay. So okay, so we'll just stay at this a little bit so that we digest. So let's draw the picture, right? So okay, suppose this is your f. So now suppose I want to find the value of this f star at y. Okay, so yeah, I have some y. Then what am I asking? I'm saying that look at every point x. So let's say this is my x, and I'm asking for the difference between f of x, which is this height, and y in a product x. Okay, so yeah, so y in a product is I don't know where, maybe it's here. So this is y product x. Yeah, and then this difference is what I'm looking at. Okay. So okay, so let's just compare it precisely for a Bundy function, just to play around. So okay, so can someone tell me, so what is f star pi for a Bundy function? So this is supremum x in R now, it's 1D. By the way, I'm confusing d and n for some reason. Okay, so I'm going to use d and n interchangeably. So let me just use n everywhere. It is n. Okay, so supremum over x in R of yx, so now everything is 1D, minus x squared. Okay, so can someone tell me what this is? Yeah, what is it? So to maximize this. So evaluate. Yeah, exactly. Yeah, y square by 4. Good. Okay, so yeah, take another example. Okay, so what if it's just linear? Yeah, so this kind of a fun example, you see a curious answer. So what is f star x again? So we just remember. Well, this is supreme. So f star y, supremum over y over x of xy minus cx. So it's a bit weird because now this x just comes out.
Y is greater than C, which is completely unavailable.
Yeah, exactly.
Actually, we are taking this for all the x.
Yeah, or x, yeah.
So it's infinity again, except when
Exactly. Yeah. So this is 0.
I think it's x star of y. Right?
Oh, yeah, sorry. 0 if y is not equal to c.
Y is equal to
Oh, so sorry, yeah, if y equal to c. If y is not c, then you can always just make it infinity. Yeah, that's why we put infinity in the range. Just for corner cases like this. Okay. Yeah, so that's a said that very funny things can happen when you take central together. Okay, so let's take one more example. So of x equals absolute value of x. Okay, so let's do this. So f star y, well, suprema of x xy minus y. Okay, yeah. So this is a bit funny. Any idea what happens here? So okay, so let's play it out. So
y is between -1 and 1, then it is 0, and then it is.
yeah, exactly. So okay, I think let's just take an example. Suppose y is half. So then, well, then this is supremum of x by 2 minus x. Right? Yeah, and then as Madam correctly said, yeah, so the mod x will dominate now. So therefore, the right thing to do is just put x equal to 0, which is 0. So yeah. So indeed, if y is between -1 and 1, then this will be 0. And otherwise, like in the previous example, it's going to be infinity. So 0. Y is actually, yeah, probably open bracket. Yeah, okay.
Close bracket.
Close bracket. Yeah. No, not really. Okay, so if y is exactly 1,
Means x minus
then x minus mod x, yeah.
So it's going to be, yeah, 0. Yeah, close
Close. And otherwise. Cool. Yeah. Okay, that is enough of 1D examples. Now let's do a high dimensional. So take something a bit familiar. So half of x transpose x. Okay, or yeah, whatever, norm of x square. Okay, let's do this. So now, what is f star y? So y is also now high dimensional object. Is it the same dimension? Then y in product x minus. So let's see. So okay. So any idea? You guys try.
No, y square.
Why?
It's the same quadratic equation of that.
Yeah. Okay, but how will you prove it? Like.
Take the derivative. Which is the derivative x equal to half by 10% is x. X equal to yeah, x equals to y. X equal to y. Oh, okay, that's a half. So that's a normal square. So now it's just normal.
Yeah. Okay. Cool. Yeah. Exactly.
No, half by.
So you get like a half.
Like half normal. Half normal. Okay.
Great. Yeah. Exactly. So you get this. Nice. Okay. And do one more. So this is kind of a famous example called negative entropy. So notice that now you have to restrict the domain a little bit. So now f is from only positive or threat to reals. Yeah. So yeah. So and now let's figure this out. So now what is f star? Like. So this is separated by and by x. Okay. So notice that this is separable. So I can break it component by component. So it's enough to. So I'll just pretend that n equal to 1. Pretend to 1. It is separable. So okay, so then there's just suprema in our yx minus x and then x. Okay, and now we have to do some calculus tricks. But I'll just write the answer. Okay, but yeah, what is it? There's no magic here, just calculus. And you can show that this is. Sorry?
E goes to 1 minus 1.
Yeah, exactly. Yeah. Should we do it right now or you answer? I mean, you take derivative and.
Yeah. Say derivative will be
Okay.
x time will be y minus
Yeah, exactly. Yeah, is it?
Log x equals to.
Yeah, okay, let's do it. So derivative by x is y minus 1 minus wait, yeah, and if it's 0, then x is 3y minus 1. And to plug this back in, then this is
This just summation y and x.
yeah, exactly. That will write the final answer. So this is
First term will be y and y to y minus 1, second term will be y minus 1 times
okay. So specifically, this will be just yi e to the yi minus 1 minus
y minus 1 times
yeah, and one of them will cancel, right? So you just get
okay.
yeah. So just
e to y.
so you get exactly this. Yeah, great. Yeah, so that's an interesting answer. So somehow taking the venture over, yeah, until it is exponential. Yeah, so this had to be isolated. So, yeah, and it's kind of the reason why you end up with this algorithm called multiplicative weights, where you have this exponential going on. So that's essentially the reason is essentially this. But okay.
Maximizing entropy mean constraint.
Sorry.
So the optimization is equal to maximizing entropy from mean constraint.
Yeah. Yeah.
So that's like a Gibbs tree.
Exactly. Good. Okay. So okay. Now let's look at some properties of this dual. Okay, so this is a very interesting plane. It's called the Young-Fenchel. Inequality. So it says that the inner product between y and x is always at most f of x plus f star y. So essentially, you can split the inner product by taking the corresponding functions. So let's see why. So actually, it's kind of simple. Let's just prove it. So okay, so let's just look at the right side, right? So what is f of x plus f star y? So now let's use the definition. This is supremum over.
So f of x is separation, then yes.
Sorry. Oh yeah. Okay, I was writing the other thing first. Right, the proper way. Supremum over x prime. Yeah, I'm calling x prime to not mix it up with the other x. Y product x prime minus x prime. Right. And now since this supremum, I can plug any value I like. So I can plug x prime equal to x. Yeah, and then it'll just cancel and cancel it. Yeah, so okay, anyway, the point is somehow this duality allows you to break the inner product into this addition. It's, yeah, cute fact. Okay, so this is like one interesting property. Another property is that F star is always convex. So this is whether F is convex or not, regardless F. And this is not hard to see. Okay, so why? So let's see. So for any x, I can just think of the function gxy, which is y in a product x minus of x. And why is it useful to think of this? Because now I can pretend that I'm just taking a max over all these functions. So now f star y is just supremum gxy. And now you know this property that supremum of affine functions is convex. Okay. And finally, there's kind of this acute but useful property, which is about conjugate, I mean, whatever, dual of what about separable functions. So, okay, so suppose my function is separable in the sense that I have function f from function two variables now. So, but it's separable. So f of x1, x2 is f of x1 is f1 of x1 plus f2 of x2. Okay, so then you can show, just by writing it down, that the group are separated. Then f star of x1, x2 is f1 star. Sorry?
F star is y1.
Oh yeah, sure. Yeah, I think I'm just using notation a bit. y1, y2. Yeah, I decided to solve because you didn't take supremum, right? Supremum is just split. Yeah, so like in a particular split and second ones. Okay. Okay, and there's another cute property, so the most fun. So this is called the so f star of star. Okay. This is what do you think it is? Yeah, dual of dual should be the function. Yeah.
Like convex lower order.
Yeah, exactly. Okay, so if you so this is not f but the convex lower bound. Yeah. Okay, so but if you assume, okay, so let's just assume just to make it look nice. So this is equal to f if yeah, okay, so finally one more. So and this kind of how we will use okay, I won't prove this. I think this kind of nice, but the one thing which I wanted to do last is about gradients. Okay. So it turns out that the following is short. Following are equivalent. Yeah, and this kind of the important part. So suppose y is a subgradient of f at x, then x will also be a subgradient of the dual at y. And in fact, your Young-Fencher inequality will be tight. The following are equivalent. Okay, so yeah, so this is kind of interesting because it also kind of tell you a way to find these gradients because the third inequality is right. So if you know one gradient, then you can pick the other one. So let's okay. So let's do this. So, okay, so let's prove one implies third. Okay, so suppose y is a subgradient. Okay. Now, what can I say about? Okay, so well, okay. So now let's write down f star. So what is f star y? Raised supremum over. Here, now let me call use different symbols for du y inner product du minus f of u. Right. And now, what do we know about subgradient? Yeah, exactly. So, any subgradient satisfies that f of u is we'll put it the other way around. Oh no, I think that's strictly satisfies f of u minus f of x is, so there's a picture, so here is my x. So suppose this is my function and this is my x. So then it should be a non-differentiable function. Okay. So now if this is a subgradient, y, then it must be the case that if I take any point u, then f of u minus f of x, this must be at least inner product between y and u minus x. Yeah. Okay. So now if I manipulate this a little bit, then I get, okay, so u minus f of u is most, so right, and this is exactly what we have. So since so therefore this is always at most. right? And now if you just manipulate this, then you get this, and then that gives you product X is at least f of X plus y. And now if you remember the previous inequality, yes, right? So now if you close that and get equality. This plus financial, yeah. Quality, you see. Okay, so that's all good. Okay, now let's prove 3 implies 2. Okay, so okay, so remember I have to show that X is a subgradient. Y, right? And we know that the eventual inequality is right. So okay, so let's see how to do this. So the point is that okay, so let's pick any vector v. So for any v. So what is f star v? That is sigma over u. Right. And now this thing here is at least right by yeah. So it's because it's true for every I get to plug equal to X. So essentially, I'm reversing the previous proof in some sense. So now I plug equal to X, and now essentially by a similar trick as the previous proof. So now I guess write this as v minus y minus f of X plus yeah. So now yeah. This thing here, right? This is nothing but v. Oh, sorry, so, oh no, okay, okay. Now I use this equality here. So right here. So this is v minus y plus f star y. Okay. Yeah. And now I'm done. Clear. Why? So remember, I have to show this. So now let's just write it the other way around. So f star v minus f star y. Remember, this is what you care about. So now this is exactly, in fact, v minus y. Oh, yes, yeah. So this is equal to, yeah, v minus y. Yeah, that's it. Yeah, I think it is essentially the same to that. So here I wanted to end here somehow. Yeah, so sorry, here going 3 from 1. I started from here, then I ended with this thing here. I just kind of did the other way. So here, so I start with this duality, then yeah, I plug u equals x. Then, yeah, and then I use equality, and then I get the subjective. Essentially, okay. Okay, so we get one more that. So that goes. So now we have to prove 2 implies 1. So, okay, so we have given, so we know that x is separating f star at y. So okay, so now I know that f star is convex. We showed this earlier. So now if yeah, so now if x is separated of y, then it means that yeah, then yeah, and now I can plug my third thingy, right? So wait, sorry. Okay, cool. So no, sorry. I'm a little confused. Oh no, okay. So I think the point is to use that goal of the goal is a function itself. Okay. So the point is okay. So yeah. So let's call G as f star. So just to make it kind of more obvious. So let's just write G as f star. Okay. Then G is convex. Okay. So now if x is a gradient of G at y. Okay. Now I can plug the previous thing. So remember, I've called 1 implies 3. So now I apply this, but for G instead of F. Okay, so now apply 1 implies 3 with G instead of F. Okay. Yeah, so what does it give you? So it gives you that.
G of S. G star.
Yeah, so so inner product of y and x is G of y. So sorry, G star y plus. No, so yeah, so we have also switch x and y, right? G star x plus G of y. Okay. And now I use a dual of dual as dual. It's a function. So first I do this. Okay. Yeah, but here this is all of x. So G is perfect.
No, we didn't use FS.
But we find subgradients and
I mean,
that we should not do it.
no. So G forms regardless of the FS forms. Yeah, so that would say that G star is G. Okay. Not S star.
Right. Okay. Cool. Okay. So let's look here. Sorry. So okay. Cool. So G's we have just true. Okay.
Then if we are assuming that it's correct. Yeah, we're using subgradients there.
Yeah.
Yeah. Okay. Yeah. So I guess they will read that. Okay. Great. Yeah. Yeah. Okay. So I think maybe yeah. Cool. I should have done this somewhere. So. Or this water straight this. Yeah. So I will write this. Which is the otherwise so see thanks. Cool. Okay. Yeah. Yeah. And now you just to revert to the same argument.
You might not have and might not exist.
Yeah, might not exist. Yeah. Yeah.
Might not exist, but if it exists, we call it a subgradient.
I guess what is that convexity is equivalent to the existence of subgradient.
Okay, everywhere.
Everywhere, yes.
Yeah.
Yeah.
No, but the thing is, 1 to 3 you could have shown by just assuming existence of a subgradient at a point.
Right, at a point, yes.
But that doesn't imply like it's convex.
Yeah.
They will practice.
Yeah. 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 So I guess if you want the whole thing to work, then
They may maybe
good. Then you need subgradient everywhere. Oh, okay. And now you just repeat the previous argument.
It could happen that if you started with a non-convex.
Yeah.
And for some points that get installed exist. And then for those points you won't have a 3 equal and you won't have
Then you want
Lower convex equivalent.
yeah.
So I guess the general statement is if lower convex equivalent, smaller equivalent.
No, the online will still go because it's just that you won't have 3 implies 1 because 3 will never be satisfied for those points. So at the point it will still those things will still hold true. Wherever your subgradient exists, then you can take it up on y, then the YFL type for that.
Yeah.
And for those points where so when you are lower convexifying a function, at some points this your envelope will match the function.
Yeah,
In that case, this will
exactly.
And whenever it doesn't match, this will not work, none of those conditions.
Yeah, I was just saying, condition equivalent with the F to replace with the lower convex. Lower convex equivalent.
So this thing will work, but it's just that, in addition to also, if you have the F is convex, you also have that for every X, you have some Y which makes everything true.
Yeah.
Which may not hold if you're, if it's not, if your F is not convex.
Yeah.
I guess you're consistent.
Yeah, we are.
Okay, great. So I guess it's good things to see. Okay. Okay. So now let's define the idea for divergence. So in particular, to talk about a particular divergence called the Bregman divergence. Yeah, maybe some of you already know this, but this will show so many places. It's good to see it again. So literally, the Bregman divergence is the difference between the function and its linear approximation. So if I have a function f, so let's make it, yeah, so f is, let's say, convex. Then the Bregman divergence between x and y is, so you take the linear approximation of f of x by y. So which means that I take the value at y and I take the gradient at y. So by convexity, this is always non-negative. Cool. So well, why is this interesting? I guess it leads to many interesting definitions. So say some examples. So suppose f is, yeah, say the usual norm squared. Okay. So well, let's figure out what this is. So well, don't even know what this is. So this is, yeah, 2 norm square minus 2 y minus y. I just took the gradient at y and multiplied by x minus y. But this is just, yeah, exactly, because this becomes, yeah, so one of the two goes here, becomes positive. Then you get this. Sorry. So it's, yeah, as stated. Yeah, so this recovered the usual distance. Cool. Let's do one more, which is, yeah, again for negative entropy. So yeah, does anyone know the answer? Yeah, so this is to clear divergence. Okay, probably is right the answer. So you can just write the terms out, and you get xi ln xi by yi minus alpha norm of x plus alpha norm of y. So this is what you get, and this is also known as, yeah, this is the with general QL divergence. The general because typically x and y are distributions, and then these other norms are one. But if it's not one, then this is the general definition. Great. Okay. Okay, great. So, and then I just try to one or two more examples just to complete the picture. Few more. Yeah, so this you maybe have not seen. So one famous kind of convex function on matrices is trace of x log x. Yeah. So again, here you take the space of PSC matrices. So actually, strictly, yeah. Okay. So yeah. So for and then yeah. So this is like the matrix analog of the negative entropy. Yeah. So then you end up with yeah exactly. So it's not called matrix divergence, but yeah. Then it's called one. Yeah. So but it looks very similar. So this is x small y log x minus x log y. So this is like your first term, and then you get minus x plus y. It's like your second, yeah, remainder. Yeah, and as pointed out, this is called here von Neumann divergence or entropy. And yes, and quantum people also call it quantum entropy, quantum relative entropy. Yeah, I guess it goes by many names. Yeah, so this is another famous example which comes somewhere. And I'll take like let's just put like one word for completeness. Different colors. So f of so another famous convex function is minus log determinant. So so then you end up with trace of x y inverse minus identity minus log determinant. Okay, so you end up with this, and it's also called the log determinant divergence. Yeah, so saying all this so that if you see it in some book somewhere, it's paper somewhere, then capture it. This is, yeah. Okay, yeah, it's different examples. Okay, yeah, guys, yeah, enough. This okay. So now let's look at the properties. So so what about convexity? So it turns out that this is actually convex. In which argument? Let me just write down. Just recall what it was. So this is yeah, exactly. So
Try to use better way than linear function.
yeah, linear stuff here. And it may not be convection by. So yeah. Cool. And now let's talk about the. Okay, so I'm not also the f is differentiable and everything. So assume differentiable. Yeah, and convex also. Now, yeah. So remember now I want to understand the interplay between this fragment divergence and the pencil dual from earlier. Yeah. So let's see that now. So gradient of f star at so let us recall this, right? So if I take the gradient of f star, the gradient of f at x, then what will I get? There's no this is x. This is from the equivalent properties from the book. And because here is differentiable, so some gradient is generally gradient. So yeah, so that's this thing. Good, this we know. Okay, but now first where does the fragment divergence come in? So the fragment divergence between x and y is the fragment divergence of f star.
If it's differentiable in convex, does it mean f star is
Sorry, is
consider then f star will also be differentiable for limited lines, may not be, we will, wherever it is not infinity.
where is not infinity?
linear function example? The linear function example.
Yeah, the real function example. So yeah, so then yeah, so the other thing is one more daily condition which I've been writing is that you also assume that it's closed. So you so you remove these boundary cases. Good. Okay. So yeah, so if you make these assumptions, then okay, then next what do you expect? So it's so there's the fragment divergence of f star, but with extend by the other way around. And okay, so what should come here? Let me ask you this sequence. F star at what? Yeah, exactly. Yeah. So but
Is it
yeah, we switch that. Yeah. Grad f of y, grad f of x. Yeah. So this is the curious thinking. And okay. So let's see why. Also, I'm going to understand what's going on between dual and the primal. Okay. So what is f star at the gradient? Okay, this is okay. So this is just the inner product between the gradient. Yeah, this is by the equivalent conditions. Yeah. Because gradients will get equality. And also you get that f star gradient of y, the same thing. Right? Okay. And finally, gradient of this I already wrote. And you also have this. Yeah, and now again combine all this. So okay, so now let me write down the fragment divergence. So if you look at the Bergman divergence between grad f y, grad f of x. Okay, what is this? This is f star at grad f of y minus f star grad f of x minus grad f. Take the gradient at this thingy. No, the other one. Here, yeah. And yeah, sorry, the other one. And now take the difference. Yeah, I think it's fine. Yeah, it's fine because this first.
Yeah, y first.
Y first. So it looks the wrong way. Good. Okay. Yeah. Now let's see. So now I want to use this step on the previous slide. So as far as anything is as far of grad is grad in a product with the argument minus the function. Now let's plug that. So this is grad in a product argument minus the function minus grad in a product argument as the function.
This x.
Sorry.
X dot with grad f. I'm just gonna.
Yeah, exactly. 6. Yeah. Yeah. And now I guess something will cancel.
Grad f dot x dot cancel, then we get grad f times minus.
Yeah, yeah. So this cancels with this. And yeah, and now this just exactly what it is. Right?
X minus f of y.
Yeah, so I guess it's a cool property. Essentially, it says that in a dual space, the divergences match if you take the gradients and you split the order. Yeah, so that's like the picture. Yeah, I just write two claims which I will not prove. Yeah, just two more properties. So this is one is called the Pythagoras theorem for divergence. It says that so yeah, so it's saying that okay, look, I have these points, right? So here is x, y, and z. So now I'm looking at this, divergence between x and y plus divergence between z and x. Minus this third side. Right. So yeah. So essentially, I'm going from y to z in two ways. In the third term, I'm going directly from y to z, The first time I'm going VX. So I'm asking like how much have I suffered? And yeah, and this is in fact turns out to be exactly grad f at x minus grad f at y inner product x minus c. Yeah, okay, I guess, yeah. I'm going to prove everything, but yeah, this is a calculation. You just plug things in. Okay. And so this is one. And and another one is the gradient of the divergence. Gradient divergence. So gradient at x. So gradient with respect to x, the divergence. So this turns out to, okay, I think this you can probably. Yeah, this is grad f of x minus grad f of y. Yeah. Cool. Okay, nice. Yeah, but the star property is the one when you go to the dual. Okay, so yeah, that's really the one. Okay, great. Okay, so I think I want to do more properties. I will probably do more properties next time. But I want to start giving some examples so that you're motivated for next class. So here's a example of mirror descent and application of duality and Bregman divergence. Yeah, so I want to just give you a flavor of how all of this will get used. Okay. So let's recall how gradient descent works. So what's the algorithm? So it says that so normal gradient descent is xt plus 1 is xt minus eta times gradient of f at xt. Okay. So to motivate gradient descent and motivate variety and everything. And let's think a little bit about this iteration. So I'm starting at a point xt and I'm subtracting some scalar multiple of the gradient. So here we are assuming implicitly, because it's not written here, that xt and the gradient lie in the same space. So in our usual now, so if I have 5-dimensional RX space and I'm working with usual norms, then everything is fine. But suppose, just for sake of example, I take a different space. Okay, so suppose I wanted to do this. In a space, in a non-Hilbert space. So more specifically, suppose I wanted to do this in the what's called the L1 space. People know what L1 space is. So L1 space is the space of all vectors whose L1 norm is bounded. So any vectors could be infinite. So basically I go to infinite dimensions, but I assume that the L1 norm is bounded. It's space of all vectors like this. So now how do you define gradient now? So it turns out that you really cannot. Okay, so I mean you can, but it will not lie in the next then. So now the gradient, yeah, or whatever you will call the gradient, it's no longer the same gradient, but whatever you call it. So there will not be the usual gradient, and in particular, it will not lie in the same space. Yes, so in fact, here the right thing to use this was called the pressure differential. The pressure derivative. So yeah, so we don't use this, we use the pressure derivative. And if it derivative, but have you seen the pressure derivative? So okay, so maybe let's write down what it is. Or maybe I do it next time. Yeah, I don't want to do too much detail. Last 5 minutes. Okay, anyway, let's just say roughly the point is. So roughly the point is that we are not forced to move to a different space. Essentially, we are forced to move to a different space. And in particular, you want to move to a space where it makes sense to work with the gradients. So this is a space of gradients. And you want that whatever was true for your points in the old space, you want similar stuff to end up working in the space of gradients also. And that's why the property of the Bregman divergence, where you move to the duals and you get the same Bregman divergence for the gradients, that now becomes very useful. Yeah, so that actually gives you the way to switch between the spaces. And yeah, and this is where the interplay of duality and Bregman divergence comes in. Oh yeah, so I guess I'll just leave it here. Yeah, so yeah, so the next time we'll see how to make this more precise and how to apply it. Okay, great, thanks.